I hope the people in the audience, I'm around for a few days and I love to interact and talk to people. So, if there are things you'd like to talk about, I'd be happy to talk. 45 minutes goes quickly, or 40 minutes, so someone's going to let me know time. It goes very quickly, so I'm going to try to give an introduction to fluid mechanics that might miss some of the fine points, but hopefully will get us where we need to be. And you should ask questions either during or after. It's up to you. So I want to begin by just showing where the equations of low Reynolds number flows come from. That's what was my charter according to the organizers. And so just by way of notation, I want to say that I'm going to represent the pressure by P, the velocity by the vector V. I tend to underline my vectors, and the stress tensor by sigma, the second order tensor that's the state of stress. And because of that, you know that we need equations of mass conservation and momentum conservation. And so if we suppose we have an incompressible flow, we know the velocity is divergence free, and the state of stress is characterized by what's called the Cauchy stress equation of motion. And the Cauchy stress equation of motion relates the acceleration of fluid elements given by the density times the time rate of change of velocity using the material derivative. That relationship is given in terms of body forces and the divergence of the stress tensor. And I should say I've already ruined the beginning. I put at the beginning some classic references that everybody interested in low Reynolds number flow should know. I'll maybe mention them now. I'm sure we're going to be watching, well, I spelled video wrong, didn't I? I'm sure we're going to show you clips from this great video by G.I. Taylor that was made in the 1960s. If you haven't seen it, it's a remarkable video for many reasons, including just basic education. There are two very nice articles on this topic from very different perspectives. One is by the Nobel laureate Ed Purcell called Life at Low Reynolds Numbers, that the people who study swimming are going to talk about. And John Hinch has written a very nice article, a short introduction to low Reynolds number flows. And then there are two books, the classic Happel and Brenner on low Reynolds number hydrodynamics, and the soon-to-be classic by Babette and Jeff Morris that on suspension mechanics. Okay. And if you want more information about that, or any other references, historical or otherwise, I'm happy to share what I know. Okay, so we have the Navier-Stokes equation, or the state of stress. This is often called the Cauchy stress equation of motion. We then need an expression for the state of stress, and so most people will take the body force to be gravitational, and the state of stress will be given by a constitutive law, which, if we assume the flow is incompressible, will be of the form a pressure times the unit tensor plus twice the viscosity times the rate of strain tensor that I call E. Now, I guess one thing that will come up in this lecture is everyone has different notation, slightly different notations. I think this is fairly common. There are some differences, of course. And what you need to think about with some of this. So as soon as you do this, you need a short remark about kinematics. So kinematics telling you the state of fluid deformation. And for completeness, I'll just say that if you stand at some origin and you look at a point a distance r away and you ask what is the velocity at the point r relative to some origin, you would write that the velocity at point r is the velocity at some origin, whatever the state of the flow is, if you imagine some kind of velocity distribution plus 1/2 the vorticity cross r, where the vorticity is the curl of the velocity field. This blackboard is just too small. I'm going to be complaining throughout this 4.5 hours. We write something like this, where the vorticity is the curl of the velocity field. Oh, I'm going to try, because Basile is, where's Basile? Basile is going to be lecturing elasticity, and you're going to use U for the deformation, probably?
Well, it's going to be 1D, so the strain measures are...
Oh, okay. Well, if occasionally I write U, it's because when I lecture a typical class, I often use U for the velocity. I'm trying to use, I told myself I'd use V for this. Okay. So the vorticity is the curl of the velocity, and the rate of strain tensor is half the gradient of V plus the transpose. And many of you might want to work in index notation. I'm going to do almost all my presentation in vector notation. And we talk about the vorticity term as telling you about local rotation, and the rate of strain is what E tells us about. And that will be important in a few cases when the different lecturers tell you about how the structure of this equation applies to different problems. Okay, so if you take the stress tensor and you substitute it into the Cauchy stress equation of motion, you use incompressibility, and you insist that we'll only consider gravitational body forces, you arrive at the Navier-Stokes equations, which is the starting point for many fluid mechanical problems. So substitution, assume the viscosity is constant so you can get it outside a derivative sign, and you arrive at the equation of motion in the form rho dv dt is a body force, a pressure gradient, and mu times the Laplacian of v. And the material derivative, if you expand, has two pieces. But because we're going to be studying low Reynolds number flows, those pieces won't be important unless you consider finite inertial effects. Okay, so here's the Navier-Stokes equations. It's true that there's a body force, but it's very common in many problems to introduce what, say, the book by George Batchelor would call the dynamic pressure, which is to try to make the equation such that you can remove the body force. And you do that simply by redefining the pressure to be pressure minus rho g dotted with the position vector. Okay? And so long as rho is constant and you consider g as constant, then this substitution gives you an equation of motion of the form mass times acceleration is pressure plus viscous terms. And the advantage of this form is that if the pressure gradient is not 0, then V has to not be 0. Okay, the Navier-Stokes equations in its normal form allows V to be 0, and you have a state of hydrostatic pressure or hydrostatic stress. So the nice feature of this form is that it gives you the insistence that the pressure gradient being not 0 means V is not 0. Okay. And most of us just work through the equations this way, and we don't tell you whether it's hydrostatic pressure or not. But I just thought I'd say it just in case it comes up somewhere in some of the lectures. Okay. So this is a quick, very fast discussion to give you the form of the Navier-Stokes equations. So where this leads is, since this is supposed to be about low Reynolds number flows, is the characterization of inertial effects. And we measure inertial effects via the Reynolds number. And so just for convenience, imagine an object of typical scale L moving at some velocity v in a fluid that has density rho and viscosity mu. And consider the case where either you have a, just for the sake of simplicity for my case, consider a case where you either have steady motion or, if you like, time-dependent effects that at least can be scaled by a typical time, which is how long it takes to translate a body length, where v is just the magnitude of the vector, capital V. And in that case, you can determine the order of magnitude of the inertial terms versus the viscous terms. And you see that the inertial terms always have the feature that they're the velocity squared divided by length according to either term. They're the same order of magnitude if time is a advective time scale and you have the density. So the order of magnitude of the inertial term is v squared over length, and the order of magnitude of the viscous term is mu of velocity divided by length squared. From here, we typically just imagine that the pressure is responsible for pushing or creating the flow. The pressure is responsible for either accelerating liquid or for overcoming friction. You can think about it either way. And so you arrive at the Reynolds number, which we'll generally call Re, Reynolds number. And here's the tragedy. We're out of blackboard space again. OK, so the Reynolds number is typically introduced this way as the ratio of inertial terms to viscous terms. You'll hear myself and probably a few other lecturers, if we ever talk about narrow gaps or lubrication, we'll define the Reynolds number slightly differently. You might want to make a note if you want to talk about that with us after. But the only point I want to make is there's a slightly different interpretation of the Reynolds number that's very useful when thinking about low Reynolds number flows. And so I'll just do that very quickly. And so the case of low Reynolds number flows is the study of those problems where the Reynolds number is small. Those of you that know this subject know that this limit in some cases can be a tricky limit. You know, if you might want to ask for differences between 2 dimensions and 3 dimensions that may come up somewhere. You might want to ask for, if you make this limit, what are the order of magnitude or the order Reynolds number corrections to anything you calculate. Some of these are non-trivial questions. But nevertheless, when the Reynolds number is small, we neglect inertial effects. And so in this limit, we end up with the equation of motion that there's no acceleration, there's a pressure gradient, and there's a viscous term. And we're considering an incompressible flow. And so these are generally called Stokes equations. Some people like the term creeping flow equations. And obviously, if there were slightly more time and I was more pedagogical, I would have made the equation non-dimensional. I would have seen the appearance of a Reynolds number. Okay, so just a remark about the Reynolds number. So the Reynolds number has the form rho v length over mu. So you can write it as a ratio of time scales. And for low Reynolds number flow problems, this is a very convenient physical way to think about the problem. So you write it as, first you note that VL over nu is another way to write the Reynolds number, where nu, the kinematic viscosity, is the ratio of mu over rho. And the dimensions of nu, which many people indicate, or at least I indicate by brackets, is the square of a length over time. It's a diffusivity. And so you then notice that this equation can be written as L squared over nu, which is a diffusion time. And those that really like fluid mechanics would say, what's diffusing? And they'd say, well, it's vorticity. It's local rotation that's diffusing, and divided by L over V, which is the time to advect the particle scale, the particle length scale. And so a low Reynolds number flow is one such that the diffusion time is very fast, is much shorter than the time to change the geometry. That's how you would say it, shorter than time to change geometry. Okay, so that's just a convenient question.
Yeah, with this choice, you're always neglecting also the partial time derivative.
Yeah.
It's always steady flow.
Yeah, so the question is about the inertial term, and in particular the partial time derivative. So that can be a delicate question, but for the majority of problems, we're also assuming that the flow is, this assumption is really telling you the flow is, and I wouldn't call it steady, I typically call it quasi-steady, which simply is making the point that if you take any geometry, and let's just do this one, I have an object and it's falling towards the boundary, the geometry is always changing. The particle gets closer and closer to the wall. In the low Reynolds number flow limit, effectively at every instant of time, you're solving equation 1 because you're assuming that those unsteady features are much smaller than either the magnitude of the pressure gradient or the magnitude of viscous effects. That's an assumption. Okay? And so if you fall too quickly, that assumption breaks down. But we will use the equations of low Reynolds number for many of these problems that even include geometry change. Is that okay? But that's an assumption. Okay. Maybe I will point out that, maybe that's worthwhile pointing out, that there is a limit to include unsteadiness. I wasn't going to say this, but the limit to include unsteadiness, your name is Julia, is to say that if the convective inertial effects are not so important, you can still study the equations where you write rho dv dt. So you include a little bit you include all the unsteadiness, a little bit of inertia, and you solve what are sometimes called the unsteady Stokes equations. So these would be called unsteady Stokes. And in particular, this equation is used for many oscillatory flow problems. Okay. But again, the specific answer to the question will be a case-by-case basis. And if anyone studies, and I might mention in mine, particle movement towards walls, we'll be able to quantify when we can neglect this term more precisely.
Reynolds number, there's a microswimmer swim by high frequency. I don't think this term can be neglected.
Yeah, so if
have very high frequency.
yeah, well, that's it. That's consistent with what I'm saying, right? So the question is, if I have a high frequency microswimmer, so that's something that would, say, be oscillatory, then you at least have to include this term.
Yeah.
Yeah, well, that's why I wrote the equation. Right. But that's why I'm also saying it's a bit of a case-by-case basis that if there is time dependence in the problem, then you have to think through, is this term important to you or not? Right. And, I'm happy to talk about all kinds of, people use an atomic force microscope. That's a device for measuring surfaces. It works in so-called oscillatory mode. The studies of that problem are often through this equation. Okay. It's called tapping mode, I guess. Okay?
How smaller number should be low Reynolds number? You said RE.
Okay, so the question is, how small should the Reynolds number be to use the low Reynolds number flow approximation? Okay, so Lots of people don't like to answer that question, I guess. And you know, it's also important, and I'll try and answer it in a second. But you know, the Reynolds number involves the velocity, so there's a limit where people like to say I'm doing a zero Reynolds number flow. I mean, we all use that language. That's a slightly unusual use of language, because if it's really zero, then v is zero, and then your motion. So you always really mean low Reynolds numbers. So you know, I think most people would say if the Reynolds number is smaller than 10 to the minus 1, it's fine. Many problems involve Reynolds number 10 to the minus 2. You will see that when you compare flows where the Reynolds number is 1 and compare theory and experiment, it's often quantitatively maybe off by 20 or 30%. It's not terrible, but qualitatively it's okay. So I would typically say if the Reynolds number is less than 1, why not use it? I was caught on tape saying that. I mean that in a serious way, though, right? If the Reynolds number is less than 1, at least you have some idea that viscous effects are important. If the Reynolds number is actually 1 and someone says, please solve the Navier-Stokes equations, you can only do it with a computer. You can't do it analytically. So there's great value to trying to study these problems. Right? You don't look happy.
And do you think a low Reynolds number effect exactly equal to zero Reynolds number effect?
Yeah, I think most people use
Stokes equation to study low Reynolds number, but this is exactly mathematically zero Reynolds number. But do you
No. I was making a statement about language. This is asymptotically the zero Reynolds number the low Reynolds number approximation. This equation, you've neglected terms of order Reynolds number. But that's asymptotics. That's just saying the approximation to the Navier-Stokes equations when inertial effects are small is this equation. That doesn't mean you've set Reynolds number equals 0, as in v is 0. It's an approximation to Navier-Stokes. Okay. And so, you know, formally we could write this as a perturbation expansion. The danger with doing that is, you know, for the experts in the audience realize this, that you've neglected a term that I've claimed as order Reynolds number. And so you normally think that that should be a regular perturbation expansion because you've retained the highest derivative and killed the lowest derivative. But the experts will know that, in fact, many low Reynolds number problems, if you want to calculate the order Reynolds number approximation, is a singular perturbation problem in some cases, not a regular perturbation problem. It can be a regular perturbation problem in some cases, but not all cases. So the Reynolds number, order Reynolds number correction can be a highly non-trivial case, and it's associated with several paradoxes named after famous people in fluid mechanics. And we can discuss that also if you want, but not now. Okay? Okay, so very quickly, how are we doing time-wise? I've only used 20? Wow. It's amazing. Oh, wait a second. Going the wrong way. OK. All right. So next, I want to make a couple remarks about what I called equation 1. From a theory perspective, it's much cleaner to write equation 1 in a slightly different form. And to recall the Cauchy stress equation. So are all the questions OK? That's OK? Okay. So write 1 as divergence v is 0 and divergence stress is 0. So we write equation 1 in a form where everything looks divergence free. And the stress tensor in this form then is a pressure distribution, which I'll just remind you is really the dynamic pressure plus 2 mu times the rate of strain tensor. And so this is also Stokes equations. And it turns out for certain things we do, it's much cleaner to start with the equations in the form 2 than in form 1. The form 1 is very nice if you want to solve a boundary value problem and someone says, solve for the velocity distribution. Form 2 is very convenient if you want to understand structure of solutions. OK. What do you, okay. Okay, so I'm not going to do all of this now, but we will do some of it. So maybe I'll just say types of problems. So I'm going to answer the structure problem by now showing you something about problems. And you want to ask yourself how many of these you want to be able to solve and know the answer to. So the simplest one is you take a sphere, you translate the sphere at velocity v, and you ask what is the force, the hydrodynamic force that you need to pull on the sphere. So I should say, probably should have, I'll say it over here. So other quantities that are important. You can ask for the force the fluid exerts on a surface. And if you do that and you only work in terms of the dynamic pressure, you typically call that then the hydrodynamic force because its force is only from motion. You would take whatever surface you're interested in. You'd identify the unit normal pointing into the fluid, and you'd perform the integral over the surface n dot sigma ds. And you'd call that the hydrodynamic force. Okay. Many people write sigma dot n. Sigma's, it's the stress tensor, it's symmetric, and in the formal derivations, I've always written it this, starting on the left. And you can also talk about torques. So if you need to talk about the torque, you need to identify an origin, you need to identify a moment arm, and the hydrodynamic torque, which I'll use the symbol L. What do you use in your book? I can't remember. Is the integral over the surface. You take the moment arm, you multiply by the force per unit area. So these are forces and torques that act on surfaces. T? Well, doesn't matter. Okay. Okay, so what are types of problems? And then I'll get at this point, what do I mean by structure? So you take a sphere, you translate it in a fluid, and you ask, what's the hydrodynamic force? Many of you already know that Stokes calculated that it's 6 pi mu the radius times v, where a is the radius of a sphere. Right? And you can go through a derivation if you want. But the structural point is if you stand at a distance r, a vector position r away from the sphere, you can ask what's the velocity distribution. You can ask what is the velocity as a function of position. And by structural, I mean the velocity, it turns out, varies as 1 upon distance from the sphere. And so by structural, I mean understanding why the velocity varies as an algebraic power of distance, and in this case, why it's the power 1 over r. And the feature that's important is, yes, you can learn this by solving the exact equations by solving a boundary value problem, but you can also deduce this fact in a couple steps from the form of equation 2. So that's what I mean by structure. Okay. To show you that, okay, you're going to say, well, this is trivial. So to show you that maybe things aren't so trivial, you could ask, what if you have a cylinder? So here's a cylinder, same radius. You drag it at velocity v, and you ask, what's the hydrodynamic force? And you might think, well, cylinders are normally 2-dimensional, so that's easier than spheres, which are 3-dimensional. So what's the corresponding force? Yeah, you have Stokes paradox. So here there's a question because there is no solution to this problem unless you give me more information that tells me about 3-dimensional features. Okay, so there's a question. Here's another question maybe you know the answer to. Suppose I take your sphere. Here's a sphere, and I translate it parallel to a wall. And I ask, does it rotate? Does the sphere also rotate when it translates? When you translate a sphere in free fluid, it translates without rotation. The only way you get rotation is you apply a torque. If you translate a sphere near a wall and it's so-called torque free, does it translate, yes or no? Sure? Which way? Yeah. So it turns out yes. So you're allowed to ask how much, okay? And we can answer that question if you want, okay? So now you can combine B and C. I don't know. Maybe I'll just do it down here. I don't like to do that. So now you do the cylinder again. So you take a cylinder, you translate it parallel to a wall. Does it rotate? Okay, there's one answer, yes. Anybody else? No. Who said that? And you're saying because you want to be difficult, or you know? So it turns out it doesn't. It does not. So the answer is, for a cylinder, no. And it turns out that's independent of distance from the wall. So these are the kind of questions we can address over the next, few days, talking about low Reynolds number flows. And there are, of course, many others. But this is just to point out that they're both kind of precise questions we can ask. They're qualitative questions we can ask. And we can, in every case, try and understand why. And in this case, if you want, and there's time, I can tell you, how you do the calculation, what the answer is, and why, and draw you pictures. Okay? It's kind of interesting, right? Little known fact. So I decided every lecture, even on the well-known topics, there has to be some little fact that is new to someone. Okay. Okay, I just want to make a couple other remarks about these problems. So other problems of this type involve slender objects. You're going to hear many lectures, I think, that talk about slender objects. But the classic problem, and then we can talk about why, is you take a slender object whose radius, say, A, is much smaller than, say, the half length, so where A over L is a number that's very small. You drop the object so that it falls parallel to whatever the force is, say gravity. You orient the object the same perpendicular, say, to gravity. You let it fall. You imagine, in this case, say, sedimentation. It's just falling because of its weight. And you can ask, for the same force, what's the relationship of the fall speed when you fall with the axis perpendicular to gravity versus parallel to gravity? And at high Reynolds numbers, this ratio is arbitrarily large. But at low Reynolds numbers, this ratio is a constant times the parallel fall speed is some constant times the perpendicular fall speed. And the surprise is the constant is nearly 2. Okay? And so we'll show why 2. Okay? Other problems that come in if you want to understand Brownian motion, which was rationalized nearly 100 years ago by Einstein, then you know that the diffusion coefficient of small objects, so-called translational diffusion coefficient, involves thermal energy, so Boltzmann's constant times temperature, so the thermal energy divided by what's called the resistance. And the resistance is the ratio of the hydrodynamic force to the speed. I'm using the same notation I had over here. So this formula for the diffusion coefficient is called the Stokes-Einstein equation, since it combines the argument of Einstein and Stokes, the so-called Stokes drag on a sphere. And so for a sphere, this is kBt over 6 pi mu a. And what's known is that this formula is a good approximation even for molecules. So if you take a molecular dimension and you knew the viscosity of the solvent, you get the diffusion coefficient. So it works for small particles. It works for small ions. So there are lots of problems that involve these kind of low Reynolds number arguments. Okay. So let's see, the last things I need to say. So there's some mathematical properties I want to start to show you, mathematical properties of Stokes equations, of either equations 1 or 2. Anka, it's okay? Okay. So for the next few things I need, I'm just going to show you equation 1. So 1 is incompressibility, and Stokes equations in the form of minus gradient of pressure plus mu Laplacian of V. Okay, so if you're interested in detailed features of this solution, the first thing you do is you take the divergence of the momentum equation. So take the divergence of the momentum equation. And so the left-hand side is 0. The right-hand side is Laplacian of P. And the next term, assuming mu is constant, is Laplacian of the divergence of V. But the divergence of V is 0. And so the pressure is so-called harmonic. It satisfies the Laplace equation. So we commonly say that P is harmonic. And we know a lot, right? A lot is known about the Laplace equation. You can take the curl of the momentum equation. If you take the curl of the momentum equation, you get 0 on the left. You get the curl of the gradient of a function. The curl of the gradient of a function is 0, and so you get the Laplacian of the curl of V. So if you take the momentum equation, you get the curl of the gradient of P is 0, and then you get mu times the Laplacian of curl of V. So you get the vorticity, the vector vorticity satisfies the Laplace equation, or the vorticity is harmonic. I think I'm still using V, right? Okay. Okay, so those are those two features. There are two other things that are easy to say. But it's also important to note that because it satisfies the Laplace equation, you can often immediately write down the structure of solutions because you know about solutions to Laplace. So the next one I don't know any use for, but it's nice to write down. Well, I don't quite know any use for it, but it's nice to write down. You have like 10 minutes? Is that right? Okay. So the other things to say are, if you take equation 1 and take the Laplacian of 1, by that I mean the momentum equation, then you get 0 is minus the gradient of the Laplacian of P, exchanging the Laplacian and the gradient, which you're allowed to do because both are linear operators. Assuming mu is constant, then you get the Laplacian of the Laplacian of V. And so the pressure is harmonic, so you can kill the pressure. And so you learn that V satisfies a fourth order equation, which you might call the Bi-Harmonic Equation. So there are a few uses of this, but it's nice to write. Okay, so for completeness, I thought I should write it. But the normal way you see a fourth order operator come up in solutions to Stokes equations is in detailed problem solving. So I'll just point that out to you in a second. So when you do detailed problem solving, and I think Darren will probably show you a number of things with that. You can imagine a 2D flow. So imagine some 2D flow in a plane where you call the directions in the plane x and y. Then you need to write down the x component of velocity and the y component of velocity. And in a 2D flow, what you commonly introduce is the stream function. And you always introduce such a function to automatically satisfy continuity. So in 2D, in Cartesian descriptions, the velocity has the form dvx dx plus dvy dy is 0. That's continuity. And so you know you can automatically satisfy this equation, and that's the whole point of the stream function. You can automatically satisfy this equation if you introduce a function, the stream function, which is defined as d psi dy for Vx, and then minus d psi dx for Vy. You can put the minus sign in either place. It's strictly up to you. And psi is called the stream function, and it's a function of position in the plane. Okay. Because this automatically satisfies the continuity equation, you no longer need to talk about Vx and Vy. You just talk about psi. And to find psi, you can use the vorticity description. So for a 2D flow, what you learn in fluid mechanics is that the vorticity is only in the direction oriented perpendicular to the plane. So if x and y is the plane of the motion and z comes out of the plane, the vorticity is in the z direction, where the vorticity is given by the curl of the velocity. So the z component of the vorticity is given by the x derivative of Vy minus the y derivative of Vx. That's just kind of keeping the curl in the right direction, because x, y, z is by the right-hand rule is a positive feature of the curl of V. But Vy is minus d psi dx, and Vx is d psi dy. So this equation comes out the Laplacian of psi, and I guess there's a minus sign. And so since Laplacian of the vorticity is 0, we already saw that the vector vorticity satisfies Laplace. So in this case, the scalar vorticity will satisfy Laplace. And the vorticity is minus the Laplacian of psi. Then you see that the Bi-Harmonic psi satisfies the Bi-Harmonic equation, which is often written del forth psi is 0. So in 2D problems, because you have two equations of motion and they're both second order, you have to solve a fourth order PDE, which is the Bi-Harmonic problem. And then you go back and reconstruct everything. You construct from the stream function, you construct the vorticity, you can construct the velocity, and from the momentum equation, you construct the pressure.
Does the stream function formulation restrict 2 dimensions? Can you not do the same thing in 3 dimensions if you just say that you just define the flow as the curl of some function, then it's automatically divergence free?
Yeah, so you can. So the question is it restricted to 2 dimensions? So I'm not an expert on all these mathematical features, but if you have, for example, an axisymmetric flow problem, so flow past a sphere, which you might think is a 3-dimensional flow problem, but it's axisymmetric, so defined by 2 variables, then this same description works. If you do more generally, then you need, I don't know what you're thinking about, but there's a description of flows where you have both a poloidal part and a toroidal part, so you have 2 functions you need. Then the spirit of this holds, but not the details, so you don't end up with such a simple structure. So I'm pretty sure if you can define it in terms of 2 variables, then it's OK. Is that all right? Did I make a mistake, by the way? Tell me if I did. OK. Well, if I, OK, so last thing is a feature of what do detailed solutions look like. So I just want to point out that once you appreciate Stokes equations, when you go to the literature, there are lots of solutions. There's 100 years of solutions of Stokes flow problems for every kind of, for lots of geometries. And the structure of the solutions involves solving effectively boundary value problems. And so I just want to point out to you one way that over the years people have constructed solutions to boundary value problems of this type. And this is kind of, I might call this representation of solutions of 1. So suppose someone says to you, solve divergence of E is 0, and solve 0 is minus gradient of a pressure plus mu Laplacian of V. It's
45, so.
yeah, no. How about if I take 2 minutes and I just show this and then we take a break? Because there's supposed to be a break after this, right?
Yeah.
And I start. Oh, it's nearly 45 minutes. Okay, so just no. It's it's okay. It's okay. It's okay. It's okay. So here's a remark. Here's a remark. So note the following idea. So if R is a position vector, note that the Laplacian of pressure times the position vector. If you were to work this out, in other words, use your knowledge of vector calculus to work this out, you'd get 2 times the gradient of pressure. Let me just see. Plus the position vector times the Laplacian of the pressure. Okay, that's just a fact. I'm asking you, you can check it if you want. If you accept that it's a fact, then you realize that, well, the Laplacian of P is 0. Okay? And that means that you can guess a solution for the velocity, because the Laplacian of the velocity is supposed to be the gradient of the pressure. So that means you can guess what's called a particular solution to the ODE, to the PDE. You can guess that a particular solution for the velocity, which I'll call VP, is 1 over twice the viscosity times whatever the pressure is times the position vector. And this is a solution to the velocity field if you knew the pressure. But you know the pressure because in principle, you know the pressure since all you have to do is satisfy the Laplace problem. Okay? So the harmonic problem, which you know. And so therefore, the general solution to Stokes equations can be written as the velocity as a function of position is the sum of a homogeneous solution plus a particular solution, just like you learn in your general studies of boundary value problems, where all you ever need is solutions to the Laplace equation, where the homogeneous solution is a vector solution, but it's Laplace. The pressure is Laplace, and the particular solution is 1 over twice the viscosity, the pressure times the position vector. And so in the I won't call it the ancient literature, in the classical literature, there are a variety of ways that people construct solutions to spheres, ellipsoids, funny shapes or whatever. And often they do it by understanding the Laplace problem, which is very well studied, and then using this decomposition to generate the general solution, and then boundary conditions come in through fitting constants. Okay, so this is where I thought I would end. And if you like, there's a small generalization that's called Lamb's general solution, has this flavor. It's a slightly different way to write this, but in the literature you'll also see Lamb's general solution, and that's kind of another way to write this fact of trying to make everything Laplace and then summing it all up. Okay? All right, that's lecture 1. Now we get a break. No.